Stephen Hawking and Yuri Milner are backing a $100 million effort to explore our closest neighboring star. The concept of exploring other star systems with probes, and not just telescopes, has proven elusive for one good reason: even the fastest spacecraft would take 30,000 years just to reach Alpha Centauri, our closest neighboring star. However, investor and space project enthusiast Yuri Milner thinks it's possible to do better. He and physicist Stephen Hawking have launched Breakthrough Starshot, a $100 million program that aims to get probes to Alpha Centauri within a generation. If all goes well, the observers would reach the relatively close-by system, 4.4 light-years away, within 20 years of leaving Earth. What if another civilization at our level were sending Starshot-style probes to our solar system? Could we detect them? Would their transmitters be loud enough for us to pick up? Would their speed help or hinder detection? Is there anything we can reasonably do to improve our chances of detecting them? Visually, it would be very unlikely to be detected. Even a sail of significant size would only be detected by luck and coincidence. That is about to change, though, as a significant effort is invested to increase Planetary Defense Stage I, detection of objects, mainly asteroids heading for a collision course. Interplanetary communications are likely to be highly directional, to maximize received energy and minimize losses. Unless the probe antenna's lobe, the direction of highest transmitted energy, happens to cross the Earth, and we happen to have a sufficiently strong antenna, of the right type of comm system, pointed in the right direction, we would not be able to detect it. Speed actually helps detection, as fast-moving objects are much more likely to be detected on a background of fixed stars. Thus, what we can do to increase detection likelihood is exactly the same as what we do to increase detection likelihood for life-threatening asteroids: invest in planetary defense. Note that the term sounds much more Independence Day-like than it actually is. Suppose we can't detect the probes themselves. This seems at least plausible: they're very small. Can we detect the laser? The Starshot folks are saying they're going to use a pulsed laser. If the alien laser is pulsed regularly as ours will be, we've got them those alien Magellans. According to this, high-quality laser beams have a divergence of less than 1 milliradian. Let's assume the alien Starshot people use a beam with a divergence of 0.1 milliradians. This is the alien counterpart to Stephen Hawking we're talking about here, only the best. The width of this beam is supposed to be around 13 feet at a distance of 35,786 kilometers from the Earth. So how wide would it be at a distance of 4.4 light-years? About 4 billion kilometers across. This is wider than the orbit of the Earth, meaning if someone on Alpha Centauri aimed their laser at our Sun, the beam would be wider than the orbit of Jupiter. This means we could see it at any point in our orbit. And if it pulses with a regular pattern or a calculated pattern which allows for better penetration of the interstellar medium, interstellar dust, this might as well be Morse code from aliens. There would be no doubt that pulsed laser light was of artificial generation. With a little number crunching, the source could be traced back to the generating solar system. This situation is one that our current SETI search would completely overlook. They do not monitor coherent light. Part of the problem with the Starshot probe is the undiscussed mass change as the speed increases. Taking a postage stamp chip to 20% of the speed of light would increase its mass to beyond the point of any propulsion being viable. If tiny probes were whizzing through our solar system, we would probably only know it when they collided with something, creating a flash that our telescope systems would perceive. By the time a Hubble or other high-power telescope could point at the spot, it would be gone. Not having solar cells or power systems due to the weight would mean that they could not transmit with any power to be detected above the noise of solar and planetary radiation in our solar system.